So I have my sample means for my 5 different random samples of 5 pennies each. So my sample means are 8.4, 12.2, 9.4, 13.6, and 13. Your sample means probably do not match mine. For part G, really want to look and see what phenomenon are we looking at, where these are not the same from sample to sample. And it's right here. It's that idea of sampling variability. Remember, every time you take a sample, there is going to be a possibility of getting a different sample statistic. The next part, we need to use technology to calculate the mean and standard deviation. We use our calculator in order to do this. So in my calculator, I'm going to start off by going to Stat, and I'm going to edit, and I'm going to clear my list. I have just a list of numbers here. So I'm going to go ahead up to L1 and then hit clear, and then go back down, so now my list is cleared. I'm going to enter my 5 numbers into this list, and then you'll do the same with your 5 numbers. And once I have my 5 numbers in my list, I'm going to go Stat, over to Calculate, and then 1 variable Stats. I hit enter, and I want it to be on list 1. I have a frequency list there. I need to delete that because I don't want any kind of a frequency list. I just want to do 1 variable Stats on list 1. And I tell it to calculate it, and it gives me the mean of my sample means, and it also gives me the standard deviation of my sample means. So for me, X bar, remember X bar is your sample mean. This is the mean of all of my means. And then this S sub X, this is my sample standard deviation. Remember, this is the one we use because this is the one that goes with our population. We have a sample, we use our sample standard deviation. So mine are 11.32, and my standard deviation was 2.29. Now this is where we said, what if our sample size was larger? What if we actually had a sample size of 25 instead of 5? In order to calculate that mean, it would actually be the same as the mean of all of my 5 means. So this is the number that everyone reported out to me in class, and I recorded them here in a Google Sheet, and then I used that to be able to graph them. I'm going to zoom out here. Oh, we can see the whole graph there. So this is the graph of those sample means. Now we have quite a bit of variability. This graph definitely still has some skewness. It doesn't look nice and normal, but it is less skewed than our population is. If we look back and we compare this to the graph of the population, here's the graph of that population. This one is very skewed right. We have a lot of data right here and very few out here. This one is still skewed, but it definitely is not as closely skewed over by 0. Instead, my lowest was a 7, and my largest is up here around 26, 27. Okay? So once we finished looking at that, we then said, okay, what if we want to take more samples? What if we want 500 samples? That is way more samples than we are going to be able to do using our class. So what we started with was we used the applet, and you have a link to this applet, but I printed out the pieces so that we can compare them. And zoom in one more time. The first part for 14.2 is we want to look at taking a sample size of size 1. So if our sample is size 1, then what does it look like? So we just took 1 penny 500 times. And if I look at this graph and I compare this to the population that I'm taking it from, they are very, very similar. Let me zoom out here. They're not perfect, but it definitely is skewed right. So there are a couple of things that you're going to be asked to report, and I'm going to summarize them here at the end. You're going to be asked to report the mean and standard deviation of each output of our applet, and then you're going to ask to be able to produce the shape of this. What is the shape of this distribution? Well, this distribution is skewed right. And remember, this is a sample size 1. Okay? The next thing they want us to do is to be able to have a sample size of 5. And if we look at a sample size of 5, what do you notice is happening with the shape of this graph? This graph with sample size of now 5 instead of a sample size of 1, this graph is no longer as skewed as it was before. It still definitely has a little bit of skewness. Here I overlaid the normal distribution so we can see that it definitely has some skewness out on this side. We have a lot more stacked up over on this side than we do coming out here. So this definitely is slightly skewed, but it's not very skewed. It's closer and closer to being that normal distribution. And if we look at our mean is still about the same. Now, the book reports that the population mean of those pennies that we're sampling from is 12.264, and that the population standard deviation is 9.613. Now, if I look at these, with my sample size 5, my mean is 12.386. That's pretty darn close to my population. But my standard deviation now is 4.549. That is not close to what my population standard deviation is. When I had a sample size of 1, if we look back, that standard deviation was 9.395. That's pretty close to what that population is. But when we increase our sample size, our standard deviation changed pretty drastically there. So, what do you think is going to happen when we increase our sample size to 25 now? Well, here we go. With a sample size of 25 now, we can look at our graph and we notice it's lost most of its skewness. It's not nearly as skewed as it used to be. And if I look at my mean is still right around 12.2, just like my population, but my standard deviation is now 1.923, much, much smaller. The last one that we want to look at is a sample size of 50, which is right here. With a sample size of 50, my mean, 12.2, it still is right there, but now my standard deviation has gotten even smaller. Now this is 1.301. So it's even smaller than it was before. So we have a table that we can report all of this out on so that we can say this is what we have for each part and be able to compare them. Let me grab it here. Here it is. And this is, I believe, part H in your classwork. Yes, for part H, this is the table that they want you to reproduce. For each of these different sample sizes, notice what is going on with our means. The mean does not seem to change much. The mean of my population is 12.264. And all of my means of my sample means, right, the center of that sampling distribution, they're all right around 12.2. Some of them are a little bit farther away, but most of them are pretty darn close to what we wanted there. Our standard deviation, however, definitely changes. As my sample size increases, my standard deviation decreases, which at this point, that should be expected because we know that the larger the sample size, the less variability that we expect, so the smaller the standard deviation. Now, the shape of that sample size 1, it matched the shape of my population. The sample size 5, it was definitely a lot closer to being normal, but it still had a little bit of skewness. The larger the sample size got, the closer and closer we got to having that approximately normal distribution, which is what we want. So this is what it looks like if we have a skewed distribution. The next question that comes up is, what if it's not a skewed distribution? What if instead we have a uniform distribution? So the next distribution that they wanted us to look at, this is change. So for this sample, the population is looking at amount of change that people got back in terms of coins. So it's going to be somewhere between 0 cents back and 99 cents back. Right? So we looked at sample sizes of 15 to see what it would look like. Now remember, with a sample size of 1 and a sample size of 5 with that skewed distribution, it really matched our population. This is a sample size of 15, so it's larger than those, and look at what happens. Now, when I overlay the normal distribution, we can see it still is not quite normal. We have a whole lot going on up here. There's more data here, kind of spread out, and then here, it's not perfectly normal. It doesn't match it quite as well as we would like, right? But notice, the mean of my population is 4.98. This is 4.96. The standard deviation of the population is 2.89 though, and this is 0.074. The next problem wants us to increase it to a sample size of 50, and think about for a moment what would happen to that mean and standard deviation. Chances are our mean will probably stay the same, or at least similar, and our standard deviation is probably going to get smaller if it follows the same pattern as before. And if we notice, that is exactly what happened. I'm going to zoom in here. Go to this one. Let me focus real quick. It's kind of blurry. There we go. So the mean here is 4.99, which is right about 4.98, right about my population mean. My standard deviation now, though, is 0.039, so it's much smaller than it was before. But notice how much better it fits this normal distribution. It doesn't have as much grouped up over here on the sides. It's much nicer and a lot smoother of a distribution there. So at this point, we've noticed enough to be able to figure out what our central limit theorem is. So the central limit theorem for means. Central limit theorem for sample means. I need to zoom way out here. Now, when we looked at the central limit theorem for proportions, remember also known as the CLT, the very first thing that we looked at was we looked at what are the requirements in order to be able to use this. And the first requirement is the same as the first requirement for a sample proportion. And we have to have some sort of randomness involved. We have to have a properly conducted sample in order to be able to use the data from it. If we have a convenience sample or any type of bias in our sampling method, we are not going to be able to apply the central limit theorem. If you remember back with proportions, our next requirement was based around the idea of our sample size being large enough. Now, we have the same idea showing up with means, except there's a slight difference. So we have to have one of these two things hold true. So either our sample size is greater than or equal to 30, so we have to have a large sample size, or if our sample size is small, our population must be normally distributed. Our population must have that normal shape, which you can look at your sample and determine if it looks like your sample is normal, or you could also just look at and see if it's given to you in the problem. A lot of times it will be if your sample size is small. If our sample size is small, it has to have that normal population, or the population has to be normal, because remember, if it was skewed right and we had a small sample, our distribution had skewness to it. So we want to make sure either our sample size is very large or our population has to be normal. Okay. Now the central limit theorem tells us several things about the sampling distribution, sampling distribution of sample means. Okay. It tells us about the shape. It will be approximately normal. Okay. I'll scoop that up. It tells us that the center, remember that's the mean of all of your x bars, the mean of all of your sample means, is going to be right around your population mean. Whatever the mean is of your population, that's where your sampling distribution is going to be centered. And we also have the spread of our distribution. Remember, spread, we talk about the standard deviation of our sample means, And the formula for that is the standard deviation divided by the square root of n. So this is what the central limit theorem will tell us to be able to move forward. So if we look back at the table that we had of all of our pieces, let me grab it here. All of the ones that we've looked at so far, if I have a sample size of 50, right, let's go ahead and look and see what our sampling distribution tells us with that central limit theorem. What should our actual standard deviation be? Well, this is sigma divided by the square root of n, so I've got 9.613 divided by the square root of 50, and I end up with approximately 1.359. Is that pretty darn close to what we got using our simulation? Yeah, is it perfect? No, but that's because it's a simulation, right? With that sampling variability, unless we have an incredibly large number of samples, if I was to take 2,000 samples, it would just get closer and closer to what this hypothesized number is. The next step that we looked at is, can we actually use the central limit theorem? Can we use it to be able to say things about our population and to be able to calculate probabilities for a sample? So if I look at problem 14.3, this is where we're starting to look at body temperatures for normal, healthy adults. It tells us that the population of all healthy adults, they have a mean body temp of 98.6, a standard deviation of 0.7, and they tell us that it is normally distributed. So if I want to sketch that distribution, to sketch a well-labeled graph, that's where that normal distribution comes in. So my center is here at 98.6, and remember, when you're sketching using that normal distribution, you go over 3 standard deviations on either side. So this is 99.3, this is 100, this is 100.7. Going backwards, I've got 97.6, 97.2, and 96.5. Now, what we want to do is we want to be able to find the probability that a randomly selected healthy adult has a body temperature between 98.5 and 98.7. Okay, so using my graph, 98.5 is really not very far away from my mean, and then same thing here on the other side. Now, using what you know about the normal distribution, can you find that area? So you have to remember, you have to find a z-score, right? And then you have to use your z-score and the tables in the back. Now, one question that you really want to ask yourself is, does the central limit theorem apply here? Do I have to use any kind of a formula for my standard deviation? And the answer to that for this part is no CLT. And the reason why is we have just an individual, right? We just have an individual, not a sample mean. So you really want to think about, what is your observational unit? In this case, because we're just sampling one person, the observational unit is the person, and then the variable is their temperature. Now, remember, for z-score, it's equal to observation minus the mean divided by your standard deviation, right? So for my first z-score, I've got 98.5 minus 98.6 divided by my standard deviation of 0.7. And for my first z-score, I get approximately 0.14. And then for my other z-score, I actually end up, or no, this one was a negative 0.14. My other z-score is a 0.14. They're both 0.1 away from the mean, just in opposite directions. I can use the table to find the mean of everything from my higher one back. then I can subtract away this extra piece. I end up with the probability is equal to 0.1114 using my table. Okay? Now this problem at this point should be something that you're familiar with. Okay? This is just simply review of topic 12. The next idea says, okay, well, what if we actually have a sample of a randomly selected sample, and my sample size is equal to 130. Can I use the central limit theorem? And we have to think back on the central limit theorem's conditions. Do I have a simple random sample? Well, they tell us that it's a randomly selected sample of 130 healthy adults. And then, is my sample size greater than or equal to 30? And the answer is yes. Now, even if my sample size was less than 30, this would still have the central limit theorem apply because we know the population is normally distributed. But in this case, all that we care about is we have a large sample, so we can use our central limit theorem. Now, the central limit theorem tells us a lot about our distribution of sample means. Remember, all of these little pieces in here, they now represent X bars. It's just a bunch of sample means in there. So we know that the shape is going to be approximately normal, which is why I just used my stamp, right? The center, so the mean of my X bars is going to be equal to the mean of my population, which in this case is 98.6, which is right here, 98.6. And then the spread, this is the one where we have to do a little bit of calculation. The standard deviation of my X bars is equal to the standard deviation divided by the square root of n. So I end up with 0.7 divided by the square root of 130, which is approximately 0.06. You can keep more decimal points if you want, but you really don't want to round any less than that. So using this distribution, I'm going to make my nice labeled sketch. So 98.6, I add 0.06 as I go this time. So this is 98.72. This is 98. Wait, no, that wasn't 72. This was 66. Sorry. 66, 98.72, and then 98.78. And then going back the other way, this is 98.54, 98.48, and then 98.42. So comparing this, I'm going to zoom out so I can look at these distributions at the same time. Comparing these two distributions, we notice the top one has a much larger standard deviation, so it's much more spread out. And remember, every piece inside of this represents an individual person and their body temperature, right? Down here, it is much more tightly compact. I know that these are the same size, right, because I just used the same stamp. But this one goes from 96 to 100. This goes from 98.42 to 98.78. We don't even leave the 98s here, so it's a much, much smaller distribution. Now, if I want to find the probability that a sample mean is between 98.5, remember these are X bars now because I'm looking at a sample mean, and 98.7, when I shade that on my graph, I notice 98.5 is right about here, and 98.7 is right about here. And when I do my calculations, I end up with a z-score of negative 1.67 and a z-score of a positive 1.67. I end up with that total area being approximately 0.905, 90%. It's a much smaller or a much larger probability. Okay? These are the types of questions that you're going to have in your homework. The important idea that you want to make sure that you're looking at is, does the central limit theorem apply? Do I have a sample mean that I'm concerned with and I'm looking at a sampling distribution, or is it just an individual that I'm concerned with? If I have a sample, then I need to check those conditions, make sure the central limit theorem applies, draw my picture so I know what my sampling distribution looks like, shade, and then use that same technique from topic 12. Okay? Thank you, and remember, if you have any questions, just send me a message and I'll see what I can do.